All right, this one we are going to talk you through roller coaster physics involving potential and kinetic energy. And we're going to use this general outline to make sense of what's taking place in terms of potential and kinetic energy. Remember that potential energy is a measure of an object's energy based on its position. So P is going to equal m times g times h, where kinetic energy is going to be the amount of energy that's identified within the object that's in motion. So it's going to be Ke is going to equal to 1/2 mv squared. So here it goes. So solving for Pe and Ke, we're looking at the location of A, B, C, D, and E. So I'm going to be able to just talk about it conceptually first. In the picture, you can see that at the location A, the roller coaster is all potential energy. And at location E, the roller coaster is all kinetic energy. So therefore, as it travels within A to E, one is losing Pe and gaining Ke. Well, actually, that's not always true, because here it's going from A to B, it's gaining kinetic energy. But then as it goes from B to C, it actually gains kinetic energy to here, and then it's losing kinetic energy and gaining potential energy to get back to C. And then from C, it's losing potential energy and gaining kinetic energy, and then from D, it loses its remaining potential energy, and at E, it's all kinetic. So consider location D. If it's halfway down the ramp, it's half potential energy and half kinetic energy. Whereas location B, if it's 1/4 of the roller coaster's path downward, it has 3/4. It's still 3/4 of its height up, so it still contains 3/4 of its potential energy, yet it has converted 1/4 of the potential energy into kinetic energy. So remember, the total energy at all of these locations must equal the total energy that it starts off with here at location A. So we're going to be applying numbers and values to this scenario here too. So here goes. Roller coaster physics. So consider a car on a roller coaster. The car's mass is 400 kilograms. It starts at rest at point A. Point A is 15 meters above the ground. Point C is 10 meters above the ground. Point B, the car is moving 10 meters per second. Point D is 5 meters above the ground. And you can assume that friction is negligible and this illustration is not drawn to scale. So here goes. The gravitational potential energy at point C. Well, point C we talked about up here, or at least it's information provided, is 10 meters. So Pe is mgh, 400 kilogram mass, times 10 meters per second squared, that's g, times 10 meters is 40,000 joules. The kinetic energy at point D in E, well, if I look at E, E is going to equal, it's going to be all kinetic energy at E. It's going to be the same kinetic energy as it was potential energy at A. So really, to solve for kinetic energy, I solve for potential energy at A. So Pe is equal to mgh, 400 times 10 meters per second squared times 15 meters is 60,000 joules. It's 60,000 joules at A of potential energy. It's 60,000 joules of kinetic energy at E. At the highest, what is the height of point D? Well, there's a couple ways you can solve this, but I could just look up here and say, oh, point D is 5 meters above the ground, so therefore it is provided. But there's a process that I can go through. The total potential energy minus at A minus the total kinetic energy at D is going to be 60,000 joules minus 40,000 joules, which means it has 20,000 joules of energy left. So Pe is equal to mgh. Solving for h, I get 20,000 joules divided by 400 kilograms times 10 meters per second squared equals 5 meters. So I can calculate it. This one just happened to be provided though. So the velocity. So velocity is going to be a product of function of the kinetic energy. So Ke equals 1/2 mv squared. So V is going to equal the square root of 2 Ke divided by m. So the square root of 2 times 60,000 joules divided by 400 kilograms gives me a velocity of 17.3 meters per second. And then last but not least, so here was a scenario that we got to in class. So I've got A, B, C, D, and E again. The roller coaster has a mass of 500 kilograms. At point A is 60 meters off the surface. Point B and C are 45 meters off the surface. And D is 30 meters off the surface. So D is halfway. So what is the potential energy at A? Well, A is going to be 300,000 joules, mgh. D, because it's halfway, it's lost half of its height. It still retains half of its potential energy. So 1/2 of 300,000 joules is 150,000 joules. And at the Pe at E is 0 joules, right? It's no more potential energy. It's all kinetic. So what's the kinetic energy at A? Well, A is going to be 0 joules. It's 0 kinetic. It's all potential. At C, now follow with me because a lot of you had problems with letter C. Letter C is 45 meters above the Earth's surface still. So that means it's 3/4 of 300,000 joules in the form of potential energy still. That means only 1/4 of the total energy, 1/4 of 300,000 joules, is kinetic energy. So 1/4 of 300,000 is 75,000 joules. What's the kinetic energy at E? It's going to be the total energy. The kinetic energy at E is going to equal the potential energy at A, so 300,000 joules. And last but not least, what is the velocity at E? The velocity at E is going to equal, so V, if I isolate and solve for KE equals 1/2 mv squared, V is going to equal the square root of 2KE divided by m, which gives me a velocity of 34.6 meters per second. Hopefully that helps.